Should I start?
Okay, let me introduce you.
Yeah.
Okay, so I'm very pleased to introduce Dr. Tarak Maity as our seminar speaker today. He received his PhD degree from the Indian Institute of Technology at Kharagpur in 2020, and has joined the Indian Institute of Science for his postdoc since then. He's an expert on dark matter physics, and today he will tell us about dark matter indirect searches using cosmic gamma rays and neutrinos. Okay, so Tarak, please.
Thank you very much. Thank you for the introduction. Welcome everybody. Welcome to my talk. First of all, I'd like to thank Professor Datta and Professor Srigari for giving me the opportunity to speak here. So as you can see, the title of my talk is Indirect Searches for Dark Matter, Gamma Rays and Neutrinos. This is quite a broad topic. However, what I'd be focusing on is on these two work that I have done. This one I have done with Ranjan, Abhishek and Akash, and this one with Devojit and Tirtho. Recently, Tibet AS experiment, which is a ground-based experiment, has observed sub-PeV gamma rays from the galactic disks. So in first part of my talk, where I will be talking about high energy gamma rays. What we will be looking at in the context of that result is the decaying dark matter scenario. And in the context of neutrinos, what we will be looking at is the neutrinos that will be produced from the dark matter captured in a galactic population of neutron star. And prospect of detecting those neutrinos in gigaton experiments like IceCube or KMCNet. And what we will see that in both of these scenarios, we will be able to probe new properties of the dark matter, so to say, dark matter standard model coupling. With this, so let me go ahead. So several astrophysical and cosmological observations firmly suggest that a major percentage of the energy budget of the universe is made up of dark matter. And importantly, those observations are quite independent in nature and also varies from length scales to galactic to extragalactic to cosmological length scale. And what we know is around 27% of the energy budget of the universe is made up of dark matter. And this is typically represented by this kind of pie chart. Having said that, we know very little about what it is, what the dark matter is, but what we know is it should be cold in the sense that its velocity should be much smaller than the velocity of the light. That's a non-relativistic. Also, it should be noted that there are certain scenarios where it could actually be warm. It has to be stable. It should not have any decay, or it has to be very long-lived in the sense that its lifetime should be much greater than the age of the universe. And indeed, we will see that one of the scenarios that I will be discussing, the dark matter lifetime is indeed much greater than the age of the universe. And it has to be massive because that's how we get to know about it. And allowed mass range is quite wide. It depends on whether you are taking dark matter as particle in nature or some composite object. If you take it as a particle, it depends on whether it is scalar or whether it's fermion. But broadly, around 90 orders of magnitude in mass is allowed. And in this mass range, around tens and hundreds of GeV, there is this celebrated WIMPs. And in this mass range is the sub-GeV dark matter and ultralight dark matter, which are of current interest. And there are these ultra heavy and heavy dark matters, and also you could have primordial black hole dark matter. So in this talk, what I will be focusing is in a PeV scale dark matter. So the main assumption that I am making over here is this dark matter is in, let's say, PeV scale, and dark matter is talking to standard model state by some way or another. Given this, so throughout my talk, I would not consider any kind of model. We would be only talking about things in model independent fashion. So the bottom line here is I'm I'm taking a PeV scale dark matter, which is talking to standard model state in some way. Given this, how could you probe these things, let's say collider? In collider, what you do is you collide to standard model state and produce, let's say in the context of dark matter, let's say produce dark matter. And you observe those things by, let's say, missing energy or missing energy plus associated standard model state. But since I'm talking about dark matter in hundreds of TeV and PeV scale, those are given the current energy range of the collider is kinematically dispowered. You could not produce those such heavy dark matter in collider. And in the context of direct detection, where you measure the recoil of a standard model state by the scattering of ambient dark matter, as you could imagine, this direct detection rate is proportional to the number density of the dark matter. And since the local dark matter energy density is almost fixed, so as you increase the dark matter mass, to have the fixed energy density, you need to have smaller number density for the dark matter. And as direct detection rate is proportional to the number density of the dark matter, so your dark matter flux is getting decreased. So that's why the sensitivity is going to decrease. So in the PeV scale, although direct detection could probe, but the sensitivity is quite not that much good. The cross section that you are going to probe in this scale is not quite large. And in indirect searches, what you do is you look at the patches of favorable patches of the sky or dark matter dense patches of the sky, where dark matter may annihilate or decay to produce standard model state. And by looking at the signature of those standard model state, you predict about dark matter standard model coupling. And in the context of heavy dark matter, that would be extremely useful, that we'll see. So in indirect searches, you could use several particles like gamma rays, neutrinos, proton, electron, positron. But in my talk, what I will be focusing on is two such scenarios where I will be looking at the gamma rays, high energy gamma rays that have been observed by, let's say, Tibet AS gamma experiment, and the prospect of decaying dark matter in prospect of exploring that decaying dark matter in the context of the Tibet AS gamma experiment. And in the other part, where we will be looking at the neutrinos, the neutrinos that will be produced from the dark matter captured in a galactic population of neutron star. And by observing those neutrinos, we could really probe a new region of the dark matter parameter space. This is the outline of my talk. First, I'll try to give a theorist view of this Tibet AS gamma experiment. I mean, what it is observing and how is it observing and what we are trying to do. Given that the Tibet AS gamma experiment has observed sub-PeV gamma rays from galactic disks, the question that we are going to ask whether any new physics could be probed by that experiment or not. Specifically, what we'll be talking about is this decaying dark matter scenario, and we'll see that through this experiment we could probe a new region of the dark matter parameter space. And in the context of neutrinos, we will be looking at dark matter capture in a galactic population of neutron star. Again, here also we'll be able to probe new region of the dark matter parameter space. Then I will conclude. So with this, let me start this. This is a traditional slide on Tibet AS gamma experiment. This is the view of this Tibet AS gamma experiment. It is situated at Tibet, China. It is around, this is a Chinese-Japanese collaboration, and it is situated around 4,300 meters above the sea level. The effective area of the experiment is almost 1.5 of the effective area of the institute where I am giving the talk, Mitchell Institute. Each of the white colored thing that you could see over here is actually a scintillator detector. There are 597 such scintillator detector, each having area half a meter square. What the scintillator detectors do is following. So this a cosmic ray comes, interact with the atmosphere, and it produces a air shower, something like this. And this scintillator detector is trying to absorb those air shower, the particles like electron, positron, and gamma rays. As I said, so this is this Tibet gamma experiment is looking for high energy gamma rays. So you need to have a efficient discriminator so that you could differentiate between cosmic rays and gamma rays. Cosmic rays are mainly protons. So for that, what they are doing is they're kind of hybridizing this ESR thing with muon detector. The black square thing that you could see over here is exactly same as the white color thing that you have seen in the previous slide. That is like scintillator detector. And in this 4 green panel, below each of the scintillator detector, there are water Cherenkov muon detector, which are placed 2.4 meter underground. This muon detector is quite important to differentiate between gamma rays and cosmic rays. And the result they have presented by taking this data of 719 days from February 2014 to May 2017. So before, discussing this, how this discrimination or differentiation is happening in muon detector. So let me ask the question, what is it observing? Again, as I said, so the answer is high energy gamma rays. And why are you interested in high energy gamma rays? Because high energy gamma rays are not reflected by the intergalactic magnetic fields. So it could point back to the source. And so that's why it would act as a great messenger for both for cosmic rays. So what I've been trying to show over here is a possible hadronic source of such high energy gamma rays. Let's say this is a cosmic ray source, which a priori you don't know. Cosmic rays is mainly proton. Once it produces, it will be deflected by intergalactic magnetic field, so it will travel in a zigzag way. And once it interacts with the nucleus of the interstellar medium, it could produce charge and neutral pions. These neutral pions essentially decays to photons, and when these photons comes to the atmosphere, that would produce shower something like this. And this is what you are trying to observe in the Tibet AS gamma experiment. Another motivation to observe high energy gamma rays is this. If you observe, let's say 100 TeV gamma rays, that must produce within our galaxy because something called attenuation. So, and if you observe that 100 TeV gamma rays, that essentially indicates a galactic origin of the scale cosmic rays. So there is a factor 10 difference. If you observe 100 TeV gamma rays, that actually corresponds to around PeV scale cosmic rays. So the bottom line here is to understand the cosmic ray physics. Having said that, so how Tibet AS gamma experiment is differentiating between a photon and proton shower. So here in the left figure, what I'm showing is shower that will be produced by a primary gamma rays, and in the right figure, shower that will be produced by a primary cosmic rays. Gamma ray comes and interact with the, let's say, atmosphere nucleus, and it will produce electron and positron. Essentially, what you are getting over here is electron, positron, and gamma rays. And in case of cosmic ray shower, along with this electron, positron, and gamma ray, you also expect to get muons, neutrinos, and kaons. And in the context of Tibet AS gamma experiments, these muons are quite important because that's what they have used to differentiate between these two showers. By looking at these two figures, you may assume that the gamma ray shower doesn't have any muon, so this should be easy. But that is not the case because occasional gamma P interaction would give rise a similar hadronic shower similar to this one. So you need to have an efficient discriminator so that you could differentiate between these two showers. So just to emphasize the point a bit more detail, what I've been trying to show is the air shower that would be induced by, let's say, 200 TeV gamma rays is given in this figure, and gamma ray shower that would be induced by, let's say, 200 TeV proton is given in this figure. So the electrons, so the red color lines represents your electron, yellow color lines represents positrons, and blue color lines represents muons. So this is done by simulation, and so the important point here is muons, the electrons lose energy more efficiently as compared to muons. That's why they could not travel through the ground, but muons could travel through the ground. That's why it could reach the underground water Cherenkov muon detector and produce Cherenkov light. And other important aspect over here is if you compare these two plots, you would see that there are more number of muons in this proton shower, but there are less number of muons in this gamma ray shower. So that's what this Tibet AS gamma experiment has used to differentiate between these two. And another, further, what they did is the muon spectrum that would be produced by a gamma ray shower would be quite different from what would be produced by a, let's say, proton shower. So what I've been plotted here is the number of muons, let's say above 1 GeV, and let's say the probability of getting that number of muons. So let's say if you consider, let's say 100 number of muons, probability of getting that muons from the gamma ray shower is almost around 1. But the probability of getting that number of muons from the proton shower is quite small. So what essentially you could do is, let's say if you put a muon cut over here, that means you would only consider, let's say 100 and less number of muons. That means if you put a muon cut over here, so then you are only taking 20% of the gamma ray flux and rejecting, let's say 10 power minus 5% of the proton shower. So essentially what you need to do is you need to put an optimized cut so that you get rid of most of the background proton, and what you are left with is gamma ray flux. So by utilizing these two facts, that the gamma ray shower are muon poor, and the spectrum of the muon spectrum that will be produced by gamma ray and proton are quite different. By utilizing these two facts, Tibet AS gamma experiment has actually put optimized cut so that you get rid of protons, and that have been depicted in this figure. So what have been plotted here is energy in the x-axis and survival ratio in the y-axis. So let's say if you take the energy, let's say around hundreds of TeV, at that energy, the survival ratio of the proton is around 10 power minus 5 or 6. And the corresponding survival ratio for the gamma rays is around almost 1. So this is how they get rid of proton, and what you are left with is photon. Along with this, what Tibet can do is to measure the arrival direction of the photon. So in these three plots, they have actually tried to point out the arrival direction of the photon. They have presented their result in this 3 energy beam. Like the first one is 100 to 158 TeV, second one is 158 to 398 TeV, third one is 398 to 1000 TeV. And in each of these figures, the shaded region is the region that Tibet AS gamma experiment cannot look at. So, and this black solid line is actually the galactic plane. This is something called equatorial coordinate system. That's why it looks like this. Further, so each of the blue points that you could see over here is actually denotes the arrival direction of the photons that they are observing in this energy beam, in this energy beam, and in this energy beam. And again here, along with blue points, you can see that there are red points. These red points are actually associated with some known TeV sources that is already there. And what their claim is, most of their blue points are not matching with red points. That means the blue points are not associated with any source. That's why you could call it a diffuse source. That point again have been further emphasized in this figure, where distance to the closest TeV sources is plotted in the horizontal axis and number of events in the in the vertical axis. And you could see that distance to the closest TeV sources is almost around 1 degree in the sky. That essentially, this is like angular distance. You could really convert to the linear distance. So the bottom line here, you observe gamma rays, and what they observe is the diffuse gamma rays, because the gamma rays that they are observing mostly are not associated with any source. So the next thing that astroparticle physicists should be interested in, what is the observed flux? So that again have been presented in this manner by the experimental collaboration. In these two energy beam, in these two region of view of the experiment, the first one is this one, and second one is this one, with L and B are the latitude and longitude. What have been plotted here in the horizontal axis is the energy of the gamma rays, and in the y-axis is the observed flux. And these 3 red colored points is what have been observed by the Tibet AS gamma experiment, with the corresponding representative energy is 121 TeV, 220 TeV, and 534 TeV. And the different black colored thing that you could see is the gamma ray flux that have been predicted by different cosmic ray theoretical models. Like if you consider this solid line, that is the gamma ray flux that have been predicted by space independent cosmic ray model. And if you consider this dashed line, this is this dashed line, then the corresponding cosmic ray model is space dependent cosmic ray model. Those are proposed in this paper. And also you see that, I mean, these blue points are what have been observed by this Argo experiment. And you could see that within 2 decades, there are no observation points. So that essentially suggests that this is first detection of sub-PeV diffuse gamma rays. And in this energy bin, again, everything is same, like 3 data points, 3 rate data points have been observed by the Tibet AS gamma experiment with corresponding energies, say again, same as this one. And the different back color lines is the gamma ray flux that have been predicted by different cosmic ray theoretical model. And this down-headed arrow thing is actually the upper limit in the flux that have been predicted by this Kasamiya experiment. And you could see that all the rate points are actually lies below this down-headed arrow thing. That essentially indicates that these 2 regions are consistent.
Can I ask a question? This is
yes,
can I ask a question? Yeah. So
yes, sure.
So these models, like you could in principle just like extrapolate the, I think by diffuse emission you mean like isotropic diffuse emission, just from like you could just in principle take like the Fermi measurements of the isotropic emission, and that's a power law at energies that kind of go up to this scale here. So I guess the question is, like, if you took just the Fermi diffuse, well, the Fermi isotropic background, extragalactic isotropic background, which they call isotropic, would that like agree with these models here you're plotting?
So the first one is, so this is what actually experimental collaboration has presented. I mean, there are proposals for this kind of, to explain this data, there are proposals after the experimental collaboration has presented in this paper. And what you are saying is, for the extragalactic thing, that would not contribute here because of something called attenuation. Because if you have a, let's say, 100 TeV gamma rays, that must produce within our galaxy, that cannot come.
No, yeah. So I guess I'm a little confused. Maybe I should let you continue. But like, but you were saying in the previous slide that the blue points were not lined up with the galactic plane, right?
No, not galactic plane. What I'm saying is blue points are not matching with any known TeV sources. So
okay, but they're not lined
the
up
blue
with
points are not associated with any source. So that's why they are diffuse.
So so when you say diffuse emission, you mean diffuse in the galaxy, capital G?
Yes.
Okay.
Within our galaxy. Okay, I will discuss the attenuation thing. So I have not discussed the attenuation thing yet. I will discuss the attenuation thing.
Okay, you can continue. Maybe you'll answer.
Yeah. Okay, thanks for the question. Yeah. So the bottom line here is you observe diffuse gamma ray flux, and several theoretical cosmic ray astrophysical models fits relatively well with your data. Then the question that we were asking, whether any kind of new physics could be searched to this experiment or not. So we have explored the decaying dark matter scenario, where dark matter is decaying to 2-body standard model state, and we could not find any signal for the dark matter. Rather, what we could find is a stringent constant on the relevant parameter space. Such kind of decaying dark matter scenario actually have been explored by Professor Datta and Srikari in the context of low energy gamma ray telescope, and also in the context of X-ray telescope. So let's say the dark matter is decaying to standard model state. Then how do you calculate the flux of the particles that you are going to observe? So let's say this is the point that you are observing, and let's say at a distance r from your point, dark matter is decaying. So let's say this dV is the volume. dV is the volume where it is decaying, and the number density at that volume is, let's say, n chi. And if it is in steady state, and if the dark matter lifetime is very, very large, then the decay rate could be written something like this. And if your decay rate produce one observable particle, if decay produce one observable particle per unit time, then the number of particles that you are going to observe in a detector of area A is given by this. Now you expand this TB and you end up with this formula. And between the production and reception, if the, let's say if the particle doesn't change energy or not getting attenuated, then what you do is just do the line of sight integral and you get the number of particles that you are going to observe per unit area per unit time with this factor usually known as JDK, or sometimes it is known as D factor. But I mean, realistically, you are not going to observe, one particle per decay. Then what you are what you get is a spectrum of particles, that is the number per unit energy you are going to observe some number of particles, that is again depicted by this D and D. So you need to include that. And like in case of photon, between production and reception, it might get attenuated because of the interaction with background photons like CMB and infrared, CMB and starlight thing. So that you need to take into account. And if it is producing, let's say, extragalactic, in our case, it is not producing with in the extragalactic, but let's say in case of, if there is some extragalactic source, then you need to take into account redshift and all other things. So essentially the formula is this. So now let's discuss these two things, that is the attenuation and the spectrum of the photon. So yeah, the spectrum of the photon is let's say the sky is a dark matter which is decaying to, let's say, 2 quarks. And once these quarks get hadronized, it could produce gamma rays. And the spectrum of the gamma rays could be calculated by utilizing these two, any of these publicly available code like PPPC or HTM spectra. HTM spectra is quite recently developed. We have actually utilized the result of this HTM spectra to calculate our limits. And in our mass range of interest, the spectra of PPC and HTM spectra is matching quite well. And next comes to this attenuation factor. This is just the reduction in the flux due to the gamma rays that are producing, let's say, through the dark matter decay. And while it comes through the atmosphere or through the medium, it would interact with background photons and could produce electron and positon. This is pair production process. So this is the gamma rays that is produced by, let's say, dark matter decay, and it's interact with background photons, and it could go like electron and positon. And because of this interaction, your flux is getting attenuated. The formula to calculate the flux is given by this one. This is L is the length that your gamma ray is traveling, and lambda is the mean free path that you could calculate utilizing this formula. This NB is the number density for the background photon, either CMB, starlight, or infrared, and sigma gamma gamma is the gamma gamma interaction cross section. And if you consider this background photon as CMB, then the corresponding attenuation is given in this plot. Energy is plotted in the x-axis, and in the y-axis, what is plotted is the attenuation. And as you could see, as this L is increasing around this 100 orders of 100 TeV range, as your L is increasing, the attenuation due to this interaction is going to increase. So your flux is going to get reduced and reduced if your L is increased. So that's why I'm saying if you observe, let's say, 100 TeV photon, that must produce within our galaxy, because our nearest galaxy, let's say Andromeda, is around 750 kiloparsec away. So if the photon is coming from 750 kiloparsec away, because of this interaction, it really could not come to us. That's why this flux is getting attenuated. And in such kind of attenuation, there are contribution because of this starlight and infrared. But the starlight and infrared are the density of the starlight and infrared thing are numerically important near the galactic center, and this Tibet AS experiment is not really looking at the galactic center. So that's why we have actually neglected this part, and the contribution from this part is numerically negligible. So in our calculation, we have not included this part because of this reason. We have only included this CMB part. Once you include all these things, so then you can calculate what is the flux from the decaying dark matter. So that is let's say, differential gamma ray flux. This delta omega is your region of view of your experiment. MK is the dark matter mass, tau k is the dark matter lifetime, D and D gamma is the spectra that I just discussed. And this is this line of sight integration. And this rho chi is the dark matter density along the line of sight. This is we have taken for the timing to be NFW. And this is the attenuation due to this. This is just the attenuation factor that I just discussed. And as I said earlier, cosmic ray physics is there, and there must be some contribution from different cosmic ray models like space dependent and space independent. And I mean, we have taken 3 benchmark model like space dependent, space independent, hybrid gamma ray model. We don't know which one is absolutely correct, so that's why you have taken 3 benchmark model. Now, what you need to ensure is the gamma ray flux that have been coming from here, from this cosmic ray model and from the dark matter. You need to add those up, and you need to essentially ensure that that must be less than what have been observed by Tibet AS gamma experiment. That is given in this table, with these three being the representative energy and the corresponding flux is given over here. Once you do that, we did a simple chi-square analysis, and the result have been presented in this plot, where in the horizontal axis we have dark matter mass, and the dark matter lifetime is presented and is given in the y-axis. This is for a particular decay channel where chi is decaying to PV bar with 100% bunching ratio. And this different solid lines is what we are getting for 3 different cosmic ray models. Like this green one is for hybrid gamma ray model, this blue one is for space dependent model, and this one is for space independent model. And this dashed line is the limit that is there in the literature and taken from combination of these papers. For the for the lower masses, relatively lower masses, the limits are coming from the Fermi-Lat measurement, and in this mass range, these limits are mostly coming from the ice-cube measurement. So anything below the line is actually excluded, above the line is actually allowed. That means if these are the true models for, let's say these 2 are the true models for the cosmic ray physics, then this is the new region of the dark matter parameter space that you are going to, that you are proving through this new experiment, new results. While this is for a particular decay channel, we have actually explored several other channels, and our conclusion is that for most of the channels, our bounds are stronger than the previous limits, except the first 2 generations of lepton. And as I said earlier, we have assumed the dark matter profile to be NFW, but you could check it with the other profile. We have checked it with other profile. The point here is this Tibet AS gamma experiment is not looking at the galactic center, and this dark matter profiles are different near the galactic center. So that's why we do not observe any changes because of the changing of the dark matter profile. So that's, in that sense, you could say that our limits are robust. So with this, let me move to another complementary scenario where we are trying to get the dark matter signature through neutrinos. What we will be talking about here is the dark matter captured in a galactic population of neutron star, and those captured dark matter annihilate to produce, let's say, some standard model state. And by looking at the signature of those standard model state, we could probe the dark matter standard model interaction state. So before going to discuss that, let me briefly say a few words about this dark matter capture in a neutron star. Let's say this is a neutron star with each of these smaller circle, let's say the constituents of the neutron star, let's say neutron. And if you consider a dark matter mass of, let's say, m chi moving with velocity u, because of this steep gravitational potential of the neutron star, this dark matter particle may attracted by the gravitational potential of this thing. And near the surface, the velocity of the dark matter could be something like square root of u square plus b escape square. Now, if you assume that dark matter is talking to standard model state, let's say nuclear, then it may interact with the nuclear. And after the interaction, if the final velocity of the dark matter is less than the escape velocity of the object, then it would get trapped inside the object. This is what is known as a dark matter capture. And to calculate the capture rate numerically, so what you need is of course the dark matter flux, which is again given by this. This is the number density near this object. This is the dark matter distribution, and also it would depends on the dark matter nuclear interaction strain. Also, it would depends on how many such targets are there within the object. And also this capture probability essentially takes care of this factor that final velocity should be less than the escape velocity. Once you put all these things, you could calculate the capture rate. And once this dark matter get captured, what is the possible signature that you could look for? For annihilating dark matter, you could look for heating. So the captured dark matter may deposit its energy within the object itself, or the captured dark matter may promptly annihilate to, let's say, standard model state, and the object being highly dense, those standard model state could not get out of the celestial object. So that's why they leads to the heating of the object. And let's say in near future, you observe a old and cold nearby neutron star that could essentially probe a new region for the dark matter parameter space. These have been, people are exploring these scenarios for, let's say, last 10 years or so. Could look at these papers to get such scenario. But what we will be looking at is rather complementary. Well, let's say this dark matter get captured, and this captured dark matter annihilate to produce, let's say, long-lived mediator Y. This mediator being long-lived, so they could come out of the object and produce, let's say, some standard model state. And secondary gamma rays or neutrinos produced from those standard model state could be observable in Earth-based experiment. So this is in the context of sun, Professor Datta has explored these things in these papers in the context of sun. But what we will be looking at is dark matter captured in a galactic population of neutron star, and corresponding and those accumulated dark matter may then annihilate to, let's say, this long-lived mediator which come out of the object and decays to standard model states. And what we will be trying to looking at is the neutrinos that will be produced from those standard model states. So essentially the algorithm is this. This is, let's say, this captured dark matter annihilate to some mediator Y. Those produce some standard model states, and then you are producing neutrinos. So this kind of long-lived mediator is a generic feature in certain class of dark matter model. You could look at these papers for this models. And the time evolution of the number density of the dark matter is actually captured by this equation. Can be calculated by this equation. This is the n chi is the dark matter number density, and dn chi dt is the change in the dark matter number density with time. C total is the total capture rate. C annihilation is the annihilation rate, and this n chi square is required because you need to have two particles to annihilate, two dark matter particles to annihilate to produce, let's say, mediator. And if you assume equilibrium, that means the number of dark matter particles that are getting captured is getting annihilated, also getting annihilated. Then this dn dk t is equal to 0. Then you could calculate the annihilation rate, and the equilibrium is kind of guaranteed for neutron star. So the required mass and required cross section to get the equilibrium is quite small because of the large lifetime of the neutron stars. So that's why this annihilation rate could be calculated. Once you put this left hand side of this equation as 0, then you can calculate the annihilation rate, which should be exactly the same as the total capture rate. This half factor is there because you need to have two dark matter to annihilate to. You need to have two dark matter to get that to have the annihilation. Once you have the annihilation rate, you could calculate the corresponding neutrino flux. Let's say that's what we are interested in. That again can be calculated utilizing this equation, where tau annihilation is the annihilation rate that is regulated by the mass of the dark matter and dark matter nucleon cross section. D is the distance between the object and your observer, the point where you are observing. This branching ratio of Y and the branching ratio of Y to standard model state, we have assumed to be 100% in model independent way. And this D and D you can calculate using any of the publicly available code. And this is the survival ratio. This is related to the properties of the mediator. If it is short-lived, then there is a fairly large suppression from this factor. And if you assume to be a long-lived particle, then this factor is almost around 1. So now the corresponding neutrino flux have been plotted over here, where energy is plotted in the x-axis, and differential neutrino flux is plotted in the y-axis. These different solid lines is for actually different kind of standard model state that Y is couples to. Like this black line is for Y is couples to neutrinos, and let's say this blue line is for BB bar. And in this kind of searches, there are background components of the neutrinos, like atmospheric and astrophysical components. These are atmospheric components is nothing but this cosmic rays comes and interact with atmosphere to interact with atmosphere and produce charge spines, and those charge spines could essentially decay to neutrino. That's what this atmospheric component is, and this is this astrophysical component which is recently discovered by IceCube. These two papers, we have taken these things from these two papers, and then what we did is actually we have looked for the prospect of detecting these neutrinos in gigaton detector. So, there are few possibilities, like you could look at the cascade events, you could look at the tracked events, but we are looking at the almost around 1 degree around the galactic center. And for the cascade event, for the current experiments is, the angular resolution is quite bad. So that's why we have not taken into account the cascade events, but we have looked into account is the tracks event, that is the neutrinos comes and interact with the nucleon through charge current interaction, it produces, let's say, muon. So what I'm talking about is a muon neutrino. So muon neutrino comes, interact with the nucleon through charge current interaction, it will produce a muon. As I said earlier, so muons doesn't lose energy that efficiently, so that's why it would put a track-like signature in your detector. So those number of those tracked event can be calculated using this equation, content track event. Here P is the Avogadro number, rho is the density of the target that you are using. This is the volume, this is the time of the exposure, and this Y is related to the what fraction of the neutrino energy is going to get, what fraction of neutrino energy is going to get by the lepton that we are considering, that is the mu. And this is the neutrino flux that I have just discussed. This is charge current cross section, and this is the attenuation because of the propagation through the earth. And now to get the limits, what we do is we just calculate the number of such track events from the dark matter and also from astrophysical and atmospheric component. And to get the limit, what we did is we just equate the dark matter number of events to astrophysical and atmospheric neutrinos. And the corresponding limit is given by these solid lines. In the case of neutron star, like this black solid line is for the scenario where mediator is coupled to neutrino, and the blue solid line is for the scenario where mediator is coupled to BB bar. And this different shaded region is the bounds that is there already in the literature, like for example, this region of the parameter space is ruled out by the solar disk measurement of this hawk, again through same scenario, like where your dark matter is getting captured in the sun and produce gamma rays through these long-lived mediators. And again, in the context of neutron star, this is the limit that is there already there in the literature, and this is the direction limit. So that essentially indicates that this is the new region of the parameter space that could be probed by this kind of experiment. This is kind of projected limit. So by looking at these neutrinos, those would be produced from the dark matter captured in a galactic population of neutron star, you could really probe a smaller cross section. So yeah, that's all from my side. So with this, let me conclude. So gamma rays and neutrinos being charge neutral are actually a great messenger for dark matter physics. So we have discussed two such, we have this one scenario where we have looked at the prospect of recently discovered sub-PeV gamma rays by Tibet AS gamma experiment in exploring decaying dark matter scenario. What we have got is the stringent constant in the relevant parameter space by assumption that these kind of cosmic wave models are true. And for the other channels, what we got is for the other channels, like what we got is this stringent constant in the sum of the region of the parameter space, except the first two generation of leptons, where dark matter is decaying to first two generation of leptons. And in the context of neutrinos, what we have looked at is this neutrinos that will be produced from the dark matter capture in a galactic population of neutron star. And we see that, I mean, by looking at those neutrino, those high energetic neutrino experiment like IceCube or ChemTrinate, you could really probe this new region of the dark matter parameter space. Yeah, thank you for listening. I'm happy to take questions.
Okay, so thank you so much. So we have plenty of time to ask questions for Tarak.
Okay.
Okay.
So for this left plot, did you look at any other final states for this fit? Like you use the chi2b bar, but how about
Yes.
other, like a top or WW?
Yes. Actually, we have looked at, I mean, several final states. So our conclusion is that except for first two generation of lepton, like if dark matter is, let's say, decaying to electrons and muons with 100% matching ratio, for those final state, and also for the corresponding neutrinos, for those final state, we are not getting the stringent limit in any of the region of the parameter space, except those four states. For other state like top, W, G, Higgs, all those states, we are getting the strongest limit in the some region of the parameter space. I mean, does this clear?
Yeah, very good.
Hello?
Thank you. Yeah, it's clear. Very good.
Yeah, thanks for the question.
So can you hear me?
Yes.
Okay, great. So that's really interesting. And I'm kind of wondering a little bit more about the neutron star heating that you mentioned briefly. I'm just kind of curious if what would that look like observationally speaking? If I wanted to go looking for that happening, what would I be looking for exactly?
So, I mean, what here you need to look at is, I mean, this. So what here people try to look at is the, let's say you observe, let's say around 1000 Kelvin or 2000 Kelvin old, I mean, 2000 Kelvin neutron star. So if you observe that old neutron star, then you could really probe dark matter, I mean, dark matter neutron cross section. Essentially, what you do is you calculate the capture rate. And from that, let's say you observe a 2000 Kelvin neutron star, you calculate the corresponding luminosity from both, let's say both from the capture and from the what you can expect from by observing that 2000 Kelvin neutron star, and you that, then you will get the constraint on this, let's say, mass and cross section of the dark matter. You just need to observe that. I mean, if you really observe a neutron star of, let's say, temperature of 2000 Kelvin, then you could really probe a smaller cross section of that.
Okay, thank you.
So you just assume that the neutron stars are like distributed in some way, and then there's like a diffuse flux of neutrinos that comes from like the neutron star, this neutron star capture process, right?
Yeah, actually, we have taken the, I mean, you are talking about this distribution of neutron star. Yeah, we have taken the.
Yeah, so this is just like a diffuse, if you will, background of neutrinos or whatever that comes from.
Yes.
Okay, that comes from the capture.
Yeah, that comes from this capture kind of formalism.
Okay.
So other questions?
Sorry. Actually, I missed something really basic too. One more stupid thing about it. What you said there's a gigaton detector that you're thinking you use. So these are energies of like 10 to the whatever, 10 to the 5, 10 to the 6 GeV.
Yes.
So let's see. Is that like IceCube? Is it the current version of that IceCube? Like the bigger version of that?
Okay. So yeah. So the point here is, I mean, the main problem here is this atmospheric muons, because in the context of IceCube, actually ice cube remains below the horizon for whole time. So that's why this atmospheric muon will be very much problematic for the ice cube. To look at the galactic center, KM3 net would be better because for around probably 60 or 70% time, KM3 net will look at the galactic center through Earth. So that's why those muons will get shielded. And for such kind of scenario, and once you are looking at something or neutrinos that are coming from the galactic center, KM3 net would do better. So you could think it up as a limit for KM3 net. But you in principle can do it through the ice cube, like putting some veto. Like what people usually do is people usually consider a smaller volume of the detector so that the outer volume is actually shielding your atmospheric muons and do this kind of analysis. Of course, I mean, it depends on the, it depends on the analysis that you take into account how much rigorous your analysis is. But our comment says KM3 net would do better in case of the galactic center compared to ice cube.
Okay, yeah, I just wanted to know what sort of the what detector you were scaling up. Okay, that makes sense.
Yeah.
So I actually have a question.
Yes.
So in the annihilation scenario, I may miss something from your talk. So here, here you introduced, the mediator, long-lived mediator.
Yes.
So I guess the need for the long mediator is, it should safely, I guess well, if dark matter directly annihilates the standard particles, they are sort of the capture or the dissipated inside the neutron star or something. So I guess that's why it's needed.
Yes.
Okay.
So yeah, as I said, I mean, if this dark matter, let's say, directly annihilate to standard model states, then let's say this neutron star being highly dense, those standard model states could not get out of the object. That would lead to the heating of the object.
Okay.
So that is the scenario people have explored in this paper. So what actually we have looked at is rather complementary, where dark matter is annihilating to, let's say, a long-lived mediator, and those mediator come out of the object because of long-lived or annually interacting, come out of the object and then decay to standard model states. And you are looking at the signature of those standard model states. I mean, here the good thing that you are getting here is, I mean, you can get the current bounds also. I mean, at least in using this results of the gamma ray telescopes.
Okay.
And
so
here people usually talk about projected bounds. If they observe cold and cold neutron star, then only you can put the bounds in the context of heating.
Okay. So I don't know whether you mentioned the typical scale of the lifetime of the mediator, but I guess the life. I guess you're assuming that the lifetime is sort of
yeah, that will be fixed by this relation. If this is, let's say, this R is the radius of the object that you are considering,
right? And
if this quantity is very smaller than R, then this you will get huge suppression from here. So if it is like in this quantity is similar to R, then this is kind of ordered one number.
So by the way, so just out of curiosity, inspired by this, the mediator, the scenario. So for the decaying, your decaying scenario, is it also possible to consider the case where dark matter decays to a, let's say, mediator, the particles, and then the mediator decays to a standard amount of particles? I mean, at some point, there are
that is possible. Actually, you could really prove those things also over here. I mean, through this kind of scenario, you could really prove those, but we have not actually taken into account this mediator thing. We have just, we have taken the scenario where the dark matter is decaying to promptly toward its standard model state. You could really do that. I mean, people have actually explored those in the context of, let's say, Fermi-Lat and all other experiments, but we have not considered it in our analysis. In principle, you could do that.
yeah, at some point you mentioned that if the source point is too far away from the Earth, then it's hard detect the photon, because the photon the scatter of the CMB photons. So but then I was imagining, okay, so if dark matter particles to decay sort of the mediator decays, I mean mediator is just like let's say super long lived, and then suppose it decays to a standard particles near the Earth, then I guess then you don't need to worry about that kind of the situation, right? So then
yeah, I understand your point, but I don't know. I mean, so if you look at around, let's say, galactic center, 8.2 kiloparsec is this distance. I don't know. I mean, that much long-lived mediator, I don't know whether you will be able to.
yeah, I mean that depends on the model.
That depends on of course, depends on the model, and also, I mean, yeah, if you let's say consider, I mean, in around the galactic disk or something like that, then it has to be, the mediator decay length has to be as large as, let's say, some few kiloparsec or something like that. I don't know how much that would be realistic or something like that.
I see. Okay. So any other questions for him? So if not, yeah, let's thank him again for the nice talk. So yeah, thank you so much, and yeah, it's I guess it's already 3 o'clock, 3 a.m.
Yeah,
there.
Yeah, it's 3:20.
Yeah.
Thanks for your question and comments. Yeah.
Yeah, thank you. Get some sleep.
Yeah.
Thank you very much.
Okay, so let me
Okay.
stop